We'll get moving on with the program here, and we will hear a technical talk again from Sonny Wescott, Chief Meteorologist, CISA ISD, U.S. Department of Homeland Security. Let's do a check. We have Sonny.
Okay, do you guys hear me?
I hear you, yes, and we see your slide. So take it away.
Excellent. All right, perfect. So we're going to go through just a couple of the different application uses that weather has when it comes to surface observations, upper level observations, being able to use historic data, current data, forecast data all at once, being able to understand what it is that you're looking at, which takes quite a bit of our training, being able to differentiate noise from different pattern systems that may be moving in, different threats that may be developing. So I always start with the first graphic, which is that if it wasn't for our historic data, we wouldn't be able to show these kinds of bar graphs where we're indicating that this year is already well above normal for our temperatures. This is this year, the black line against the top 10 hottest years on record, all of which have occurred since 2010. So obviously this year being record breaking in and of itself means that our models are not going to handle a lot of our forecasts well this year. The reason for this being that our temperature determines a lot of the amplified features for our weather events, whether it's rain, wind, thunderstorm activity in the way of tornadoes and hail, as well as overall the atmospheric heating and evaporation along our water systems. So the reason that we're looking at this graphic and we're making these assertions about the models not being correct is that models take into account the current parameters and then balance them against the historics. But given that this is record breaking in and of itself, it violates our historics. And so our models will be attempting to play catch up. They'll be able to identify systems as they're developing, areas of concern and intensities above normal, but they won't be able to give definitives on the way of numbers. So more in the way of what we're used to seeing, but as our modeling has progressed, so has the hazard field when it comes to climate norms. So what we're looking at when we talk to some of our stakeholders is being able to explain these upper levels of the atmosphere all the way down to the surface, things that people can't naturally see. They look outside and they see clouds, they see that the clouds are above the buildings and it gives them a sort of vertical scope. They don't necessarily understand the full scope in which that plays, in that the upper atmospherics control all of the weather at the surface. No weather at the surface is truly local because it does need the upper atmospherics in order for a lot of these events to kick off, things like geostrophic winds, the gradients that develop the instability lifting mechanism that we need for thunderstorms. So looking at Florida is a really good example right now with the stationary boundary that's over them, allowing for multiple days of thunderstorm activity because it's pulling in moisture from the Gulf and extending it over into the Atlantic. Looking at this graphic over to the right, needing these geostrophic maps that take the millibar stacking all the way from the surface back through the top of the atmosphere, being able to explain where the jet stream's at, being able to explain that there's a compression that occurs within the atmosphere, going from the top all the way down to the surface, and that pressure has impacts on waterway systems. It can displace water, whether it's in the human body, livestock, fish, our actual water systems within themselves, but also that on the back end of the lows are these highs. And when you see any changes in these systems, really being able to explain it to them with visuals becomes very difficult versus just communicating and saying, we know that the atmosphere stacks backward. And they're like, why does it stack backward? And you have to explain to them about Coriolis effect. You lose a lot of people when you start going into the actual physics of it. So needing to be able to model it and make these pictures make sense by doing these sort of stack backs is incredibly important when it comes to forecasting. Being able to explain to people what the difference between the high and the low is. A lot of people believe that highs cause weather. And while weather is technically all events subsequently at the surface, the weather as they understand it is the thunderstorms, the wind, the hail, the tornadoes, flooding, snow, any of the precipitation movements for the most part, which are affiliated solely with low pressures. So being able to explain to them that you need that compression within the atmosphere for your molecules to collide together, to create that friction, to be able to create lightning, instability, to be able to collide heavy enough to come down to the surface, and making sure that they understand that the high on the other end brings its own litany of problems. So really needing to lean forward on the global phenomena, not just one area, because one area is typically under the influence of a high or a low a lot longer. But if you were to zoom out what we refer to as the mesoscale funnel, where you look at it from the holistic view of the globe, and then you zoom down to your local level, you're able to show them what looks like a merry-go-round of highs and lows. You're able to say these lows are going to move just like horses on a merry-go-round. They're going to go up, they're going to go down, but they're always going to go one direction depending on the jet stream that's controlling them. The control mechanism being, for us here in the US, the polar front jet. explaining that all of our storms here from the US exit to the Atlantic and go off to Europe and across the Asian continent, across Russia, into the Pacific, and then come back to us again. Kind of help people to understand that these weather events are not localized, they are a far larger scaled system. They're used to thinking of it localized because they're only reacting to it in the moment in which they need the weather to do one thing or another based off of events within their personal life. So this becomes incredibly important to explain, the physics of something, the actual implications of what it means at the surface, and then the actual visuals that they'll need in order to make it make sense for their industry, for their partners, for the supply chain movement of goods. Looking at some of the ways in which we've grown in forecasting has been a little hilarious. I've been forecasting since the days of the paper charts. So if anybody else has any forecast background, what we used to do is we would take old data and new data and overlay them on a light board, and you would trace the differences and pull off your new one and then trace that onto the next one to create a forecast map. Incredibly problematic. We would also use satellite data over our bodies of water to try to look at where systems were forming, where they might be moving towards, estimating wind data before we had surface observations in those areas, before we had installed radar systems, buoy data, ship data, aviation data, all being able to be funneled into the same or similar dashboard systems. What you're looking at here over on the right are wind barbs. So being able to look at some of the turns in the wind barbs would indicate to you if there was a high or a low. Some of the wind barbs, however, would be estimates or would be damage data in and of themselves. So sometimes you'd end up with a wind barb that would say 250-mile-per-hour winds in the middle of nowhere, and you would have to completely discount that. But you would have some forecasters who would look at that data and say, oh my gosh, there must be a tornado over the ocean right now. And your response is no, there's definitely not anything there if you look at the satellite imagery. But you need to be able to balance both. Otherwise, one piece of data may look incredibly intense, but is often combated by another piece of data. So unfortunately, when it came to forecasting at the beginning, you had to balance so many different aspects of each of your different types of data, your satellite versus your wind barbs versus where frontal boundaries may or may not be, where moisture fields may or may not be. You had to have an understanding of the topography. Where are the rivers, the lakes? Is there a mountain which can produce the lift for thunderstorms? Which side is it on from when they typically see wind? What is the soil content of the area? Is the soil a lot more moist? Is it a lot more dry? Subsequently, that can play a big role in the electric charge of some of the lightning events that come into the area. So there's a good amount of data that you have to go through in such a hyper condensed period of time to get an understanding of how to do these forecasts, especially when it came to making the forecast actionable, moving resources, allocating troops, moving heavier vehicles. As a prior Air Force lead meteorologist, this was something that when we were being taught weather, we would learn in waves. So you'd go through your first physics based course, you would learn atmospherics, you would learn solar weather, you would learn all of the correlating impacts. And then through your on duty training, you would go through every month or two additional information. How does radar make sense? What in radar are you running into on your day-to-day job that doesn't make sense? And then you would create a presentation and share it with the other forecasters. And so we created this mass network of people showcasing best tools that they found, whether it was through online hunting, such as Null School, which is one of my favorites I found during my enlistment. What it does is it gives you a globe that you're able to drag and drop and zoom in and zoom out. It's a supercomputer run model. It is not maintained at a continuous level by any forecaster or meteorologist. It is just an output that is public facing. And Null School gives you the capability of going from the surface to the upper atmosphere. And what that gives you is, as you can see on here, areas of concern. It highlights, oh, the winds are really strong right here. They're turning in this direction. It's really hard when you start to zoom in to see where exactly that is. So not all of our data sets are made with the forecaster in mind. Some of them are just composites that are beneficial. So as I've learned to look at this, having to understand, oh, the white is Great Lakes, they don't differentiate the colors between land and ocean. That can make it pretty problematic, especially if you look in the bottom left where you can see the jet stream is a variety of colors, but it's all very intense. It's very wide coverage because you're so high up in the atmosphere and those impacts are a lot larger. Looking even further over to the left, you'll notice the currents. That's actually what that is, the ocean currents that you're able to model out and look for eddies that spin off in the ocean as far as the supercomputer models it. And then you're able to look at where our low pressures may or may not be moving towards an eddy, subsequently able to amplify itself into a more severe weather system because our eddies, as you can see with the temperature, might be warmer, and that may end up fueling the development of a storm even further, which is exactly what happened with Hurricane Fiona, which crossed Puerto Rico as a tropical storm but became a Cat 5 on approach to Canada, was because it followed in line with an eddy along the Gulf current, was able to self-sustain that direction. So without the supercomputer data, we wouldn't have known that was there, because you can't see eddies from the surface, even with satellite imagery, even with your buoys. They're not necessarily easily understood without the visual data that you can provide from being able to access supercomputers. Satellite imagery is so critical, so critical. And so when we look at how our satellite imagery makes it over to us, there is a pretty notable delay on the weather side of the house from when we get weather data versus some of the private industry who pays for more of the satellite constellation development on the private sector side, which has really kicked off over the last 5 years. Similar companies like Spire and Planet are producing more in the way of micro satellites going up in constellations, and those are able to do more frequent scanning. The downside with more frequent scanning is there's more data needing to be housed, especially when you're trying to loop it over longer periods of time. So we still end up really relying on our geostationary satellites. They provide a good amount of data, whether it's during daytime or nighttime. You're able to see overshooting tops of your thunderstorms, which are incredibly cold. And in some cases, you're able to see when there's a presence of a low cloud, which can indicate different heating mechanisms or continuous precipitation like rain or snow. You would only really know this through continuous application of looking at a visual, taking a snap of it, and then putting it into a PowerPoint, showing somebody, okay, you see how this cloud looks? This cloud is yielding XYZ weather. When you see this cloud, look for XYZ weather in these areas. And then you would continuously create this internal database of imagery that triggers forecast knowledge. Unfortunately, where we're at still with weather training is this isn't necessarily applicable across the board. Is not everyone's creating that internal dialogue of retaining, I saw this one cloud do this one thing this one time, there and by, I'm going to look for it in perpetuity. So what we end up having to look at is, with all of our forecast stations, we have about 4 big monitors that face out, and what they do is they run everything from our fact sheets, where we're filling in the data, we're writing out sentences, we're saying we looked at XYZ and we believe this, that, and the other thing. Basing it off of our comparison with other forecasters in the region, they're tracking the same thing because of these reasons, these models, these upstream observations, the river system at this stage, and then being able to have right next to you your radar dock. And your radar dock is usually a couple of different small screens held on one single monitor. And within each one of those screens, it shows you everything from outflow boundaries to hook echoes, which indicate tornadic activity or rotation. You end up with velocity, which can indicate be a pre-indicator for tornadoes, can also show you just how severe a storm is before it moves into your area. You can see the outflow boundary that forms from a storm that's collapsing, which will give you enough lead time to start moving aircraft inside. You can also see things like bats and butterflies, which create a huge issue because thunder will trigger bats to flee the cave, and they flee the cave in a semicircle pattern very similar to an outflow boundary. So if you didn't know there was a cave there because you didn't know the topography, you would immediately issue a warning to move aircraft inside, even though there is no outflow boundary. So not necessarily being able to take action for every time you see a radar return, but needing to understand what it looks like when it suddenly develops. We also have training on these. As you can see, I highlighted quite a few of them that are available open source to the general public, which just showcase the different ways that you can use radar to identify thunderstorms, that you can learn radar just as a 101, why it's important to understand for topography, heights of mountains, as well as some of the different ways we use the coastal data, because our storms that are offshore, we don't have as much land-based data to monitor them for growth. So we are watching them with a greater period of time between each new data set to be able to review if it's strengthening or weakening, which is why the National Hurricane Center's products have such a large window of time between updates. You're also able to see a lot of the noise that's coming off of the main radar system over here. And that noise is something that makes it very difficult when storms move into cityscapes to be able to figure out just how large the water droplets are, or if there's hail moving into the city. We lose a lot of data as it gets closer to the actual site of the radar over time. When we come to model forecasting, we're just going to really quickly touch on the top models that are utilized, which is typically the European and the GFS. There are many sites that provide these for free, and there are many sites that provide them for pay to play. As you can see, there are a lot of models. Each model weighs different atmospherics differently, which is why we have such a variance in our modeling. So each one, let's say, emphasizes more on temperature and precipitation, while another one emphasizes more on upper level winds, surface winds, and the diurnal winds. And subsequently, you can end up with each one indicating different intensities, different total precip amounts, different moves of the storm, whether it's going faster, slower, moving further north, moving further south, which is why it's so critical to never pick a favorite. Because if you pick a favorite and you base it off solely one, then like if you looked at this graphic and you're looking at the European, you'd say, oh, okay, we're really only looking at this portion of Florida for heavy rainfall events and only these portions of the Midwest for moderate rainfall events. We're looking for these numbers ranging anywhere between 7 to 9 inches of rain across that area of Florida. However, Tampa Bay looks totally fine. And that would be your statement as a forecaster. But if you looked at the GFS, and the GFS has the system a little bit further to the north and it has Tampa Bay flooding out, then as a forecaster, you've busted on your ability to communicate to the public, to your stakeholders, and to industry that there was a threat on the horizon because you chose one favorite model. And that's very hard to argue. We do typically encourage that they balance it off of at least 3 different models. A lot of people bounce it off of 2. 2 is still relatively acceptable because it should give you a wide enough breadth to say that there are some discrepancies of note for everyone else. As you can see, we are, no matter which way that you spin it, when you do a comparison, you do not have the same hours that they're available. Some model runs update more frequently, some update on 6 hour only, and some update only every 12 hours. Some run at 1 or 3 hour intervals. So it really just depends on the model set that you're balancing. But some websites will allow you to do a side-by-side comparison for this exact reason, so that you're able to track it in real time, what the difference is between each one as you're doing your forecasting. Satellite imagery, of course, everyone's got a different website. Given that we have multispectral now, we're able to see a lot more overnight, which is incredibly helpful. Being able to zoom in and get better clarity as you zoom in is still something missing from a lot of open source apps. You're able to zoom in a little bit, but you're not able to get down to that more refined level without needing to pay subscription fees for many of these. But staying further out and being able to go back, 5 to 7 days is incredibly helpful when you're looking at tracking storm systems moving across the ocean, following that carousel of weather before they come to the U.S. Being able to isolate whether or not they're upper level or lower level winds is really helpful for whether a storm is building, where it's building, how it's building. And you're able to differentiate whether you have cirrus clouds or you have cumulus clouds, or you have something more in between indicative of continuous rainfall or developing supercell when you have gaps of dry air in it. So again, a lot of this just comes down to understanding, like for over here in the West, people may look at that and think that that's clouds when actually it's snow on the mountains that are still left over. Not a lot of it, but nonetheless very present. And they may end up adjusting their forecast because they don't know topography-wise that these are mountains. So we just look at all of these different data sets, and then we try to explain that there are sometimes overlapping concerns in them, such as with our propagation fields. We have things like the image that's displayed over here are actually the wind turbines. And you can see that the wind turbines show up on radar. And so if you didn't know that, you would look at that and wonder what on earth kind of storm system is producing very straight lines coming towards your area, but they're not actually moving. So you would need to be looking at that radar continuously over time. And if they put up new wind turbines, your area may suddenly see them on radar without being aware of what it is that they're seeing, especially in areas that never had wind turbines to begin with. You'll also notice some of the other clutter. That entire region has a lot of clutter, and so you may end up leaning towards identifying if your area has a lot of airport traffic, if it's got a lot of buildings, if there's a lot of traffic in general in that region, and then being able to explain that to your forecasters and your observers to be aware of any changes that pop up that persist. So that kind of helps you to reduce the noise as you're forecasting. And some of the end products that we get from that are useful dashboards. These dashboards can incorporate the radar, the watches, the warnings, the river systems, geospatial mapping for seismic activity, the watches, warnings, and advisories for river systems, states, oceanic. You'll notice the National Hurricane Center is overlaid on here. And you're able to zoom in even further and get down to a lot more local level for counties and interact with a lot of those icons. These are also some of the different ways that we utilize a lot of the data. So being able to have access to it and do a historic review against a future impact is really helpful here, because you'll notice that we're taking the tops of our thunderstorms, which we only have thanks to radar and satellite imagery. And a lot of that comes from our ASOSs, our automated sensors. And you're able to see over time, where have our thunderstorms begun to shift, and what does that mean in a warming world? Will they continue to shift towards the east? A lot of which in the scientific community, the belief is that the eastern half of the United States will become the new tornado alley in the next 50 years, shifting almost entirely from the central US towards the east because of these amplifying features. But the only way to know this is to be able to look at a lot of the satellite imagery and the radar data. Same thing with the cirrus clouds that form on the back end of thunderstorms. Those nice wispy clouds in the upper atmosphere actually act as a blanket and trap heat in. So they're a self-fueling cycle. So the more thunderstorms that we have, the hotter it gets. And we wouldn't know that if it wasn't for satellite imagery. So some of the end products that we water down for general society just look like this. You can't necessarily look at the frontal boundaries and know that there's a turning in the winds at the most local observation level. You wouldn't know that radar is indicating XYZ from this. You wouldn't know that satellite imagery shows overshooting tops or an overarching cloud field, but you get a general understanding of the hazards your area might experience. So you have a twofold when it comes to forecasting, being able to provide them all of the data, all of the scientific background, all of the tools and techniques and the way in which you have to consider all this data, just to be able to get them this watered down end product so that they can make a decision on whether or not they go into one area or they move resources in one direction or another. So I know that was a lot of information on just the weather side of applicable use of a lot of the different data sets, a lot of the different systems. But we also utilize that data to communicate on an international scale, especially in areas that don't have radar systems or don't know about the use of satellite imagery, being able to go over there and explain to them how this could be beneficial for crop planning, housing planning, river systems, and allocation of resources and all of that. So it's not necessarily solely for one state, one region, or even just the US. We grow as all the rest of the products grow on an international front, being able to pull from what they've got available. So with that, pending any questions, that concludes my portion.
Thank you so much, Sunny. And you can still hear us. Is that correct?
Yes.
Perfect. All right. Let's give 5 minutes for questions. We started a few minutes late. And I have one. There's not one from the audience. All right. At risk of Sunny, you had mentioned that different models weigh puts differently. I was wondering if there's a distinction between models, like we talked about underlying assumptions or propagation, underlying assumption, or weather models.
All right, so I didn't hear all of that question. Can you repeat the last couple of parts?
Yeah. Do you think about underlying assumptions for weather models when you're considering different ones and different outputs?
Oh, absolutely. Yes. So I know that the GFS, for example, handles storms, or it'll give forecasts a lot further out, but it makes a lot of assumptions about moisture movement, where the winds are going to be turning based off of current systems. So needing to watch as that updates, because something that shows up a week from now on the GFS is not there in a week. It's not there at all. It's not even remotely close. Being able to balance it and say it's really good once a storm is established. You need to have. I always tell people when it comes to tropical forecasting to not use any models outside of identifying an area of potential development. Not to use anything else until a surface low is developed, because the models do not handle ingredients well on formation, but they will once a low is developed. They have a lot better understanding on how that particular depth of the low is going to interact with all of the features around it. But on the way of highlighting, oh, a low could develop, a storm could develop here and move here, I always recommend, even if it's on the European and the GFS, to just track it as an area of potential until in the live data, an actual rotation begins. Then wait for the updated cycle and then run it off of there. There's a lot of bias in the models for areas of greater instability versus other areas that don't take into account, like the dust that comes off of the Sahara Desert. That dust inhibits tropical development, but isn't accounted for in either the GFS or the European. So it may highlight there's instability, but it may not know that there's friction field there.
Thank you. All right, let me get the mic to one other person, maybe two.
Hi, Sunny. Thank you very much for your talk. I was wondering, is there anyone currently scoring all of those models for their accuracy in a historical data set? So they predict out a certain number of days. Does anybody take that prediction and score it against actual weather formation?
So every model does claim to do that. I would, as an unbiased sort of third party forecaster, I would always put stomp that I don't necessarily trust somebody who reviews their own product. I would like to see more third party reviews. Being able to say things like, we know the GFS does XYZ well, but it doesn't do this, that, or the other thing well, which you're not going to see. Even NOAA, in a lot of their reviews of their products, are a little bit more biased, which, I think we assume in general, everybody does. Nobody wants to talk bad about their baby. But subsequently, this is a problem that I think is across all parts of the weather data field, is being able to take away, the emotional or the investment on it, and to say it does this, it doesn't do this, it does this, it doesn't do this. But if you pair it with this other thing, you can meet that missing gap. And a lot of times they want to say, well, my product is the best product, thereby you don't even need that other one. And I would argue that none of them meet the full bill as it stands. But being able to go back and compare it is definitely possible, because we have those databases. Somebody would just have to sit down and either use AI or a whole staff to do a comparison to see which ones held the best. I don't hear anything.
So sorry. Test 1, 2, 3. Hi, Sunny.
Yes,
Thank you
sir.
very much for the presentation. I really enjoyed it. I am Eric Hill with the Institute for Telecommunication Sciences, and I also participate in the ITU Study Group 3. And I noticed you had the European Center for Medium Range Weather Forecasting as a data source listed. And
Yes.
there's been an ongoing discussion in Study Group 3 about the uncertainty of that data. And I was wondering if you had any thoughts on that.
Yes. So
Thank you.
in some of the different data sets that we use, whether it's let's see, there we go. Whether it's one or the other, what we do is we like to always make sure that we're touching on as many of them as possible, because a lot of the pushback that we get in a forecast can come from somebody who does favor it. So similarly, if you go to bat in court and you want to know what their main points may be on the opposite side, they may be frivolous points, they may not be correct points, they may be XYZ, but it helps you to know that their points are going to be as such, so that you can create counterpoints. So when it comes to some of these model sets, when I say things like, I prefer this model or another model, I always caveat that you should never rely on just one. You need at least three, because if you were to, for example, rely on any one of these that are listed on here as an individualistic, and you don't know what goes into that model set, then you're essentially guessing that that model set exists because it's correct. And just like with anything else on the news or on TV, it can be created because somebody thought it would be helpful, not necessarily because it's correct. The model blend that's listed as new over there takes some of the components of 4 different model sets. So where you have a lot more in the way of composite modeling that's starting to come further forward, where they combine a handful of these different models, which just further removes you from being able to look at what's being weighed and how. So I'm not necessarily going to say, that one is bad for XYZ, but I am going to say that if you notice through use over time that one continuously misses the same thing over and over again, that it's just important to look at it to know that others are probably looking at that, so that when you say my forecast is as such, and they're like, well, that's not showing up on this one, your response can be, but it's missed 80% of the other storms this year, thereby I would not invest my time in that one. However, it does indicate this area is unstable, but it may not agree in full with the rest of the modeling. Does that answer that?
Yes, thank you very much.
Okay, great. Sunny, I think that wraps it up unless there's one final burning desire question. And I'm not seeing one. So apologies for the travel difficulties, Sunny. I hear weather was in your way.
Ironic. This is the third time this year that weather has bothered me.
Well, but thank you for persevering, and thanks to our IT team for making this happen.